Plagued by noise since about June last year, and it's been so bad that on lots of occasions DX stations are calling me and I can't hear them, and that's tragic. Anyway, I went to a lot of trouble to try to find it. I walked as far as I could in every direction with a little battery operated receiver, and eventually one day it disappeared, and I thought, that's a significant piece of information. And I found out that the boy next door was away in the Hunter Valley visiting his father. And I thought, what is there next door? And I spoke to his mother and I said, has your son got a computer? No, he's got an Xbox. Ah, okay. So when he comes back, I want to do something. I want to carry out a test. So I have a battery operated receiver, and it's a good one because it's not very sensitive, which is very useful for looking for interference, because you've got to be right on the source before you can find it. Anyway, I could find it all around the district by following the power lines and the Optus cable, but what I did find, that when I walked along their driveway, as I got closer to his boy cave, the noise got worse and worse. Anyway, I spoke to his mother and she said, oh, he's got an Xbox. So I said, okay, let's go in and try it. And as I got up close to this Xbox, you know, the noise is getting louder and louder. I said, turn it off, please, Bradley. He turned it off, and it didn't make any difference. And I said, no, not on the box, on the wall. So we turned it off and the noise disappeared. It would be nice to say that that solved the problem, but it didn't. Chuck, VK2 Sugar came along to give me a hand to look for it, and we fitted ferrite clamp choke devices on everything in that house. We've now got the noise down to strength 6, whereas before it was 10/9. But we turned off all the switches to the house on the switchboard, and the noise is still coming in on the power lines. So there's somebody else who's got something in the district. And I have found, and I was just looking then, I thought I had a photograph of some of the oscillograms that I've taken from my set of the noise, and it looks like a quenched oscillator. It looks like a superregenerative detector. And I believe this is the way that switch mode power supplies operate, and they produce a repetitive pulse type noise which is so loaded with harmonics that I can trace it as far as any receiver that I've got will go in terms of frequency, and it's absolutely obnoxious on 80 metres and 40 metres. So I've still got work to do, but I think the problem is there are so many hundreds of switch mode power supplies around my district. The subject is the suburb is being gentrified. All the old 50-style houses are being knocked down and replaced by huge 2-storey mansions that stretch from one fence to the other, and they're all loaded with computers and home entertainment devices, and most of them are run by switch mode power supplies. And I subscribe to the idea that that's where most of the noise is coming from. So there's a lot more work to be done. But I appreciate what Rob had to say, because it indicates this is where the problem is. These rotten switch mode power supplies. So if you have noise problems, start looking for them and see what you can do about it. Fitting chokes may help. Indeed, I fitted a new electronic doorbell recently. When it operates from the battery, it's okay, but when I operate it from the AC power supply, I can make the doorbell ring any time I like by calling CQ on 40 metres. And I don't need that. So I've tried fitting chokes to it, but that doesn't work. It's clear that I have to go into the power supply, into the receiving unit, the base station thing, and fit RF bypasses to the DC lead coming in from the switch mode power supply. Well, that's got nothing to do with tonight's talk, but I thought I'd fill you in because it confirms what Rob has to say. Right. Where are the pens?
On the rail.
Ah, okay. What? Okay, just have the black one for that's it. All right. The subject of this little talk tonight was the design, construction, testing, operation, and maintenance of wire antennas. There may not be time to cover all of that, but we'll start with whatever we can. Now, the first thing is design. Okay, if you're going to design a wire antenna, first of all, why use a wire antenna? Anybody got any ideas? Yeah, that's right.
And Brian's not here.
Yeah, cheap. That's the part that's where I like to come in. Ham radio doesn't start with $10,000 worth of equipment. It starts off with the antenna, and you don't need to spend $10,000 to get on the air. So it's cheap. The materials nowadays are a little harder to obtain than they used to be. Once upon a time there used to be a type of plastic covered clothesline wire made by an Australian company called Untitled. It's not, if it is made anymore, it's not sold here. The stuff we get in the hardware stores nowadays is some crap that comes from China. It doesn't have as many strands. The strands are nowhere near the size of what they used to be. They used to be about 22 gauge SWG. They're now about 24, 26. So it's thinner, it stretches more, and it's not zinc plated. So it tends to rust a lot more, but it will still work. And if you have to change it every 10 years or less, well, what the hell? It's still not going to cost you the national debt. So that's a good source of material. There are various other sources of material. I would prefer to use copper for an antenna wire, and the standard earth wire is pretty good, except that it tends to stretch a bit. Well, you can overcome that if you hook one end of it onto a telephone pole and the other end onto the tow ball on your car, and just take it for a little bit of a drive, not very far. You can turn it into hard drawn copper wire, and that's much more satisfactory. Copper, on the other hand, tends to suffer fairly readily from fatigue failure. So if you've got the money to spend, there are all sorts of special wires available. From Germany, you can get stainless steel wire with a copper core, and that's fantastic stuff. As you'd expect, if it's German, it is perfect. But it costs a fair amount of money, but on the other hand, you probably only have to put it up once. So the next thing is, what's the next thing that you have to decide in your design procedure?
Where to put it?
No, before you do that.
Bands.
Support.
The what?
Support. Hold it up in the air.
Oh yeah, that's something, but where are you going to put them? The point I'm trying to get at is you need to know how long it's going to be. Because if it's longer than your backyard, well then you've got a bit of a problem. But there are ways of getting around it. So, okay, first of all, and what determines the length? What determines the length of the antenna?
What band you want to use?
Yes, the frequency. Okay, so first of all you have to decide, geez, this pen's not too good.
Dried up. You've been talking too long, so it dried up.
There you go. Okay, thank you. Where's the cat? Huh? Okay. Okay, the frequency. The next thing is, what sort of length is it for the frequency? In other words, are you going to make it a half wave or a quarter wave or 3/4 of a wave or 3 half waves in phase? So how do you determine the length knowing the frequency? Let's say, for argument's sake, that you want to put up a half wave antenna. How do you calculate the length of a half wave antenna? Not a dog's stir.
300 divided by frequency, is it?
That might be right. I can only work in feet.
468.
468 over.
Ah, that's 468
Crawler.
over or 4. Okay, right.
Don't you have one more decision before you start this, Max? You're going to go random length or frequency?
Go and wash your mouth out in the sink. Have you heard about resonance? You know what resonance is? How many of you, put your hands up if you've ever pushed a kid on the swing? Well, resonance is where you have a kid on the swing. And here is you over here. And you push and the kid's on here. And the swing goes up and the swing comes back and the swing goes up. How hard do you have to push it to start with? Very hard. But after you get it going, how hard do you have to push it then?
Not so hard.
Not very hard. In fact, you can do it with one finger, can't you? Because you're timing it so that each time it comes back, it comes up to this high point up here, and just before it's ready to turn around and go in the opposite direction, you get ready and you apply a very, very small force to it, and away it goes, and it'll sing away beautifully with very little input from you. The same thing applies with a resonant antenna. If you have a resonant antenna, it doesn't take a lot of energy to make it work. If it's non-resonant, well, it'll work, but it doesn't work as well. So it's worthwhile trying to make it resonant. Any effort that you put into that is not time wasted. Okay, so here's our length, 464 over F. So we go ahead and we cut our antenna. Let's say, for argument's sake, I'll just get my little calculator out here.
It's in there, it's talking to you.
Okay, we're going to build a 40 metre half-wave dipole. So we put in
all clear. 4, 6, 4 divided by 7.1 equals 65.3521126. 65.3 feet. And now that we know it's going to be roughly 66 feet apart, we need 2 masts to hold it. Ideally 3, as a matter of fact, because you have sag in the centre. If you have 3 masts, you can lift the centre up where it should be, not down here, but up there. So ideally 3 masts. And you need to have slightly more than 65 feet between them, about 66 feet. So you get your wire out and you hook it up and you cut it to length and you put it on insulators and you finish up with something that looks like this. This is an insulator at the end, that's an insulator at the end. These are halyards which you use to pull it up. and in here you feed it by whatever means you've already decided to feed it. Ideally it should be coax cable, but there are other ways of doing it. Now you put it up and you check it for operation. The best way to do this, if there are all sorts of Butte instruments available, various forms of antenna analyzers, and they come in a wide range of prices. There's a relatively inexpensive one made by MFJ and it works all right. There are others which are more elaborate. They give you a computer output, which is quite valuable because you can store the results on your computer, and somewhere down the track you can do another test on it and find out if it has changed, in which case you can do something about it. But if you only have, say, pencil figures of impedance or SWR at various frequencies on the band, you've got to keep that in a book somewhere so that you can get back to it. Okay, so you check it out. And one way, the simplest way to do it, is to draw yourself a chart. This presumes you don't have some of the special gear, and you check the SWR across the frequency range. Now, the position of minimum SWR tends to be the resonant frequency of the antenna. There are other snares involved here, but let's assume for the moment that that's a perfect statement. Okay, let's say that you have already designed it for 7.1 megs. But when you did the testing, you found it wasn't 7.1 megs with your antenna. It was somewhere else. It might have been, say, 6.9. You know? This is not where you want it to be. So what can you do about it? Now, the point is that the result that you've got here is the result that you're getting at your particular installation. It's due to the capacitance of your antenna to ground, probably to the roof of your shed, or maybe the next door neighbour's shed, or perhaps his car parked in the yard. All of these things can change the resonant frequency of your antenna slightly. I had a case down in Corrosion some years ago where we were running the state gliding championships, and we had all our trailers parked fairly close to the non-directional beacon, and we got an agitated call from DCA. Something had gone wrong with the NDB. The antenna tuning unit was going bonkers, and it found out that all these glider trailers, which are some of them half as big as houses, 26 feet long and feet wide, were affecting the immediate vicinity of the antenna, and the antenna tuning unit was trying to bring them into the equation and re-resonate the antenna to take into account this sea of aluminium that was parked around it. So this brought home to me very clearly that the resonant frequency of the antenna can be determined by things other than the length of the antenna. However, you are stuck with your environment. If you have actually measured the length of the antenna, let's say you cut the antenna to be 60, what did we say it was, 65.3, wasn't it? Yeah. 65.3, and that gave you 6.9 megs. So one thing you can do some reverse engineering and calculate backwards. So in this equation, you've got a constant divided by 6.9 equals 65.3. So you multiply those two.
All clear. 6.9 times 65.3 equals 450.57.
450. So we know that in our particular environment, the correct constant to use in this equation is not 464, it's 450. So we still want the antenna to resonate on 7 megs. So we do that.
All clear. 450 divided by 7.1 equals 63.3828169.
63.38. So you know now that you have to adjust the antenna to that length. That's the simplest way to do it. You can, of course, crawl up and down, or lower the mast at each end, chop 2 inches off there, chop 2 inches off there, put it up again, do the measurements, do another curve, chop another 2 inches off here, chop another 2. You could spend the rest of your life at that. You'll probably eventually get there. But I have a friend who went through this exercise recently, and he did it 6 times. He thought, oh, to hell with it. And he cut off 6 inches at each end, and he got it fairly close to the mark. Now, in comparison with this, I had Chuck help me put up a new 40-metre antenna some time ago, and it was an off-centre fed dipole, which is sometimes called a, what do we call it, something, Carolina Wyndham, yeah, something like that. And I have grave doubts about the virtue of having an antenna which is not balanced, but in this case I needed to do it because I had recently put up a 3-element Yagi for 2015 and 10, and my G5RV was causing great problems because it was beautifully resonant at 20 metres, and it totally stuffed up the pattern of my Yagi. So I had to take down the G5RV, and I needed an antenna for 40 metres. Well, by using the off-centre fed one, I had a situation like this. Northern mast, shed, southern mast, central mast. Now, by using the off-centre fed antenna, I was able to do that. Insulator. And the Yagi, which was about here, was therefore somewhat divorced from the new antenna in comparison with the way it was with the G5RV. So it now works fantastically well as a transmitting antenna, but don't ask about the noise. Okay, so I now found that I had to change the length, so we dropped it down, we measured it so that it conformed to the new calculated length, put it up, and chucked it in, did another frequency run on it with my MFJ impedance bridge, and we found it was resonant at 7098, and I said, Chuck, that's close enough. So this technique gives you a way around it. That parameter, that 464 that you find in the textbooks, it's pretty close, but it's not the figure that you're going to get at your location. How close it will be will depend largely on all those other imponderables that the guys who wrote the antenna handbook didn't know about, didn't know that you had in your backyard. So this gives you a way around it. The next thing is that I'm reminded of a film that featured Danny Kaye. I can't remember the name of the film now. It might have been Danny Kaye Wonder Man or something like that. Anyway, he started off by saying, "This is a story, and like any good story, it has a beginning, and a middle, and an end." And that's the way it is with aerials. They have a beginning, they have a middle, and an end. And by means of coupling into one of those three areas, you can actually get it to accept power and radiate your fantastic signal all the way around the world. So you have to decide then exactly how you are going to feed it. Are you going to feed it in the beginning, in the middle, or the end? And that will determine largely the sort of feed line which you are going to use. Now, when you talk about dipoles, you tend to think about centre-fed antennas. And who can tell me what the impedance is at the centre of a dipole?
75.
75? Any more starters?
72. 72.
72? Anybody else? Okay. Well, I didn't give you all the information. The correct answer is, well, it depends. And it depends on what. I need two strong men. Advance front and centre, please.
Check the seats. Put the young bloke up.
Make sure it's level.
Close up.
Compared to Coty.
Thank you.
Is that
Now,
it?
no, not quite.
That's awesome.
Jimmy, look at
Okay, thank you very much. All right, so this is a chart showing impedance that way and wavelength this way. Now let's say that's a quarter wavelength, that's a half, that's 3/4, that's 1, 1 1/4, 1 1/2, 1 3/4. 0.25, 0.5, 0.75, 1, okay, 1.25, 1.5, 1.75. Now, the snag is, it depends on the height above ground. This not only represents impedance, but it also represents height. They're separate factors. The scales would be different, but let's assume they're both shown on that vertical scale. It works out this way. I need my two men again, please.
You need the broom.
Okay, gentlemen, I want to draw a line across there, parallel to the up a bit there, I think. Up a bit. Cool. Okay, there we go.
It's a wonky broom.
Now, when this is zero height here, ground level. If you have your half-wave dipole at a very low height, impedance is somewhere down here. Don't ask me exactly where it is, because it depends on where the real ground is. You know, if you live on the beach, that's one figure. If you live in the mountains, it's somewhere else. If you live in my place, it's about 3 feet above sandstone. So it starts off, you measure the impedance at various heights, and you get a curve that goes something like this. And in fact, this curve is like that. And the mathematicians will say that if you take that out to an infinite height, this curve here is asymptotic to 73 ohms or thereabouts. So the actual impedance depends on the height above the ground. Now, most of us use 50 ohm coax cable. Gentlemen, does this suggest something to you?
Put it up so it's 50 ohms.
Yes, give the man a go back. Okay, it may be worthwhile if you want to have it at 50 ohms. This is probably somewhere about 30 odd. So somewhere about here, there is a height which represents 50 ohms. So we tend to think in terms of the best antenna as the highest one you get. And there are sort of good reasons for thinking along that way, and I'm sure most of us would like to do that. But if for some reason or other you're one of those funny people who think that it's absolutely important to have the SWR as close as possible to 1.0, by picking a height at which it's 50 ohms, you can achieve that much more readily. And that means that it may pay you to raise or lower the antenna if you're trying to get the impedance as close as possible to 50 ohms. Personally, I have never done it, but I know people who have and claim that it was worth the effort. There is a snag here, of course, and what is that? Well, we are very fortunate to have more frequencies available to us than the armed services, and we should think about that. The point is, of course, that we can operate over a wide range of frequencies. So what is a quarter wavelength? You know, a quarter wavelength at 80 metres is about 66 feet. At 40 metres it's about 33 feet. At 20 metres it's about 16. By the time you get up to 10 metres it's only about 8 feet. So if you select this for one particular band, it's not going to be much good for the other bands. But if you want to be for a particular band, it's worth thinking about. Okay, so we can arrange it by suitably operating the height, that we can get the feed impedance as 50 ohms and not the 73 that we're all, we've learned at mother's knee. And you can feed it with 50 ohm cable and a 1-to-1 ballad, and that works out rather nicely. But what about if you don't have any coax cable or you can't afford it? Well, coax cable was known somewhere about 1940, but hams couldn't afford to buy it. Some idiots started a war, and as a result of that they started putting radio gear on ships, where it became necessary to have shielded cable up to the antenna to cut down the noise, and for various other perfectly good reasons. And when there's a war, there's always money available to do all sorts of developmental work. And probably the area where the money was best well spent was in the development of coax cable. So after the war, it became more popular for hams because we could get it in all sorts of ways, like the stuff which I had, which probably came back from Morotai, and it was green with verdigris, and but it worked after a fashion. My theory about antennas is they all work. Some work better than others. Generally speaking, we can't tell the difference. For most of us, the criterion is you put it up and you make contacts, but you don't really know whether you should be doing better by making some other changes. And if you listen around the bands, you'll hear that some people have much better signals than others. It's not always due to the fact that they are running a kilowatt. In fact, I know at least one foundation licensee up in the Newcastle area who only runs 10 watts, and he puts in a signal about 30 dB over 9. I'm waiting for him to describe how he does this, but he hasn't managed to tell me yet. So anyway, you have to decide what you're going to use for coax for feed line. I've lost my. Before the war, hams used stuff called open wire line, and it was made out of copper wire and things that nowadays you'd call paddle pop sticks, although I don't think there were any paddle pops in 1938. And I'm sure I don't really need to describe it in great detail, but you have two wires and you have a series of insulators across here. The people who could afford them in 1938 used Pyrex glass insulators, and there were some beautiful insulators made. They sort of looked like this. They were sort of a corrugated thing out of Pyrex glass, and you could subject them to a hell of a lot of strain. You just put the wire through there on one end, through here on the other end, and it took a lot of breaking, although I understand rifle fire was very satisfactory. So you can use open wire line. The surge impedance of the open wire line is a function of the spacing between the two wires and the gauges of the wires. In the ARRL handbook, which gentleman I suggest to you is probably the most valuable book that you could ever obtain, will produce a series of charts which will enable you to come up with that. You might decide you want to use 600 ohm line. This gives you certain parameters, or you might want to use 450 ohm line. And those of you who can afford it will go out to Lee Andrews and say, hey mate, I need some open wire line. And he'd say, okay, we've got 450 ohm or 400 ohm. And you say, what's the difference? Well, it depends largely on the gauge of the wire. And the stuff that I bought in America in 1978 was a single strand of steel wire. Nowadays, much better stuff is available, which is actually stranded wire in each one of these, and that comes up with a slightly different impedance figure. Now, such a design, a two-wire thing like that, which we tend to call a dipole, or some people like to call it a doublet. I think it probably should be doublet, which is French for dipole. But the difference is that whereas a conventional half-wave dipole we tend to feed with coax cable, if we're using open wire line, there is a considerable mismatch here between our nominal impedance of somewhere about 72 ohms and this, which might be, say, 600. And when you go from one frequency to another, the difference is quite large. On the frequency at which this length here is an electrical half wavelength for our half wave antenna, the impedance which will appear down here is 72 ohms. But if this is not a half wavelength, if it's say a quarter of a wavelength, the impedance which will be presented down there here is quite different. In fact, if you have a situation where you've got one impedance there, another one there, and you have a matching impedance Zm in between, say this is 70, say 70 ohms, and this one is say 600. Well, Zm is the square root of Z1 times Z2, and that's equal to the square root of 70 times 600, which is about 42,000 42,000 ohms. The square root of 42,000 ohms, unfortunately my calculator won't work that out, but you know, it's a fairly high value, and you can calculate it. Now, I worked a bloke about 2 weeks ago, and he said he was using a doublet. He said it's about a half wave on 80 metres. And I said, how about? Well, he thinks it was about 110 feet. Well, a half wave on 80 metres is probably nearer 132. So it's a non-resonant antenna for a start. I was working him on 40 metres. I said, what are you feeding it with? He said, I'm feeding it with open wire line, but I can't use it on 40 metres because the ATU keeps flashing over. And I said, really? How long is the line? Oh, it's about 30 odd feet. And I thought, oh crumbs. You know, he's got a step-up situation where he's got a very high voltage down here, and he's trying to couple it up to his ATU. He's probably got thousands of volts developed there. No wonder it flashed over. So, if you're going to use this system, you have to think about it. If that's a half-wave antenna, if you plot the voltage along it, you get something like that. Now, if this is a half wavelength of feed line, you have a low voltage here, and that will give you a low voltage down here. So it doesn't really matter what the impedance of the feed line is if it's a half wavelength long. It will repeat the impedance from top to bottom. But if this happens to turn out to be a quarter wavelength, then this sort of thing happens. That's a low voltage point up there, and down here, you know, you've got a very high voltage point. So you need a different sort of a tuner. The function of this lecture tonight is not to discuss tuners, so I'll leave it at that. That's your homework for next time. Okay, so that's the dipole, and it's probably the most universally used antenna, and it's simple. You can feed it with coax cable, even if it's slightly mismatched, it doesn't matter, it'll still work. As I said before, they all work, but just some work better than others. And in most cases, we don't have the gear to check them out. So, before we put it up, when we decide we're going to test it, what is the best sort of testing device that you can use, even before you put it up? Anybody tell me? Not a dog stirred again. Hello, you out there? There should be one in every handshake. You can get them at most hardware stores. I got mine at Mitre 10. This one's 50 metres long, and I think it cost me about $30. Probably the best investment I've ever made. You can cut your antenna to size before you put it up. If the antenna is a VHF antenna, then this sort of thing. And those devices are readily available, and they will give you the information you need. You can do your calculations based on the figures that you get in the IARS handbook. I don't apologise for using the feet system, because the IARS hasn't worked out meters yet, not properly. And most of their articles are written in terms of feet, and I can remember it that way. If, for example, you're doing the exam, once upon a time, you had to be able to draw diagrams of antennas and show what length they were and show what happens when you use open wire feed line. It's sometimes a bit difficult to remember these various equations. In fact, not too many people here could come up with the correct result. So there are two things that it's worth remembering. The first one is that a half wave at 7 megs is equal to about 66 feet. So when we go back to our equation where we have K over F equals L. If you remember that, and you know the frequency, that's all you have to remember, and that gives you your parameter. Much the same thing applies at VHF. If you remember that 144 half wave is about equal to 19 inches. The same thing applies here. L equals K over F, the parameter divided by the frequency. So 19 inches equals L over 144, or maybe 146. You know, you multiply those two out. Let's say we decided it's 146.
All clear. 1, 4, 6 times 1, 9 equals 2774.
So this constant here is 2774. I happen to know that's not right. I think 2640 is closer to the mark. So maybe that was not 146 megs, maybe it was 144. Let's try again.
All clear. 1, 9 times 1, 4, 4 equals 2736.
2736. Okay. That's interesting. Anyway, that's the basic principle. But before you do the exam, find out what the ARRL says that factor is. Obviously, I didn't remember it correctly.
Max, that's a quarter wave you've got up there, not
A quarter wave, yeah, that's right.
19
Absolutely.
inches. 19
Absolutely.
inches is
It
quarter
should have
wave.
been 38 inches. Yeah, should have been 38 inches. Yeah, thank you for picking that up. All right. So, the half-wave dipole is probably the most commonly used antenna. But nowadays, as we heard earlier tonight, there is a problem, and that problem is noise. Now, it is said that a loop antenna is much less sensitive to noise pickup because it's basically picking up the energy from the magnetic field as distinct from the electrical field. And probably the most convenient way to build a loop for those of us who only have little backyards is to use the delta loop. And the virtue of that is that you only need one mast. Now there are various ways you can build it. You can make your antenna like that. You can feed it up there. You can feed it there. Feed it there. Feed it there. In other words, it has a beginning, it has a middle, and it has two ends. Such an antenna has an input impedance of somewhere about 100 to 120 ohms. I mentioned earlier that I'm now using an off-centre fed dipole, and that has an input impedance of about 120 ohms. And to cope with that, I use a special balun which has two transformers in it. The first one converts from 50 ohms to 120 ohms. The next one goes into a 1-to-1 balun. So it comes out 120 ohms and goes into the antenna feed point at 120 ohms. I am, however, not happy about the idea that you have a transformer here which is producing outputs plus or minus allegedly the same figure, and then you couple in it into an antenna which by no stretch of the imagination is balanced. I find that a bit difficult to cope with, but it obviously works. And I think once again it comes up with the fact that they all work, some work better than others, and generally speaking we can't tell the difference, because mine certainly works for transmitting. Okay, now getting back to our loop, which allegedly is a lot less sensitive to noise, and I haven't personally managed to to verify this feeding yet. The question is, how long do you make it? Well, it needs to be about 1 wavelength long. But there's a problem. It's a closed antenna. If you have an open antenna such as the half-wave dipole, where is the snare? It's called end effect. You know, you've got this thing here which has a finite impedance, somewhere about 3,000 odd ohms, maybe at the end. This is quite different. It's not open circuit at the end, it's a continuous antenna. So end effect is different in this situation to this situation. So 1 wavelength loop, it doesn't conform to the other dimensions you've made. In fact, for 1 wavelength loop, it's roughly this. So if you want to make up a delta loop for 7.1 megs,
1, 0, 0, 2 divided by 7.1 equals 141.1267605.
141 feet. Now, what would you have thought that 1 wavelength would be at 40 metres? What did we calculate was a half wave earlier?
65. wasn't it?
65, exactly. So that was a half wave. So you would think that if 65 was a half wave, what would the full wave be?
130.
Yeah, but we've just calculated, what was it, 141 feet. This shows the difference between the end effect, which we had to consider in the case of the half-wave dipole with open ends to a closed loop antenna. The feed point is about 120 ohms. Exactly where you feed it will depend largely on where the major polarization will be. If you feed it here, it's largely horizontally polarized. If you feed it up here, it will tend to be largely vertically polarized, and down here it probably can't make up its mind. That may be an advantage because there may be directional effects. It may be that if you feed it here, directivity tends to be that way. How can you check this? There is a method which is available to all of you, and I would say probably none of you have thought about. And that's what I'm trying to do tonight, to help you develop the capacity to think about these things. Does anybody have any idea what I'm alluding to? Okay, not a dog stirred. I think it would be true to say that every one of you here would be entitled to operate on the 2 metre band. 144, 148 megacycles. Let's say, for argument's sake, that you want to put up a loop for 20 metres. I know some of you can't operate there, but this will give you the incentive to work towards it. You divide 144 by 14.2. What's the answer, roughly speaking? 10. Exactly. So that means that in your own backyard, you could very easily make up a loop antenna of this type, cut it for 144 megahertz, and then go around with the field strength meter and investigate the performance. if you had, say, a sheet of galvanised iron underneath it, you could simulate a perfect earth, and then you could raise it and lower it, and you could see what happens to the field pattern. I look forward to hearing that somebody here has tried to do it. It's been done before. In fact, it is the technique used by the National Bureau of Standards when they come up with a design for a new antenna. They do their modelling probably at microwave frequencies because the measurements are a lot easier and they have access to perfect antenna ranges. We don't. We have our backyard, or maybe we have a fielder. There's one club, I think, that every year they go to Alice Springs or Inaminka or somewhere, and they play with all different sorts of antennas, and they investigate the effect of different sort of feed systems and heights and so on. You can do that in your own backyard at 2 metres. And as I said before, I look forward to hearing somebody say that they have done it. Now, there are, of course, other sorts of wire antennas, and at some stage of the game, most people come up with the idea of using a vertical. That's not a bad idea, you might think. Why? All right. Yes, the idea of using a vertical, because it doesn't need a lot of real estate. Have you ever visited a broadcast station? Where do they have their antennas? Out in some bloody big paddock, frequently in the middle of a swamp. Why is it so? Well, I think that a standard broadcast transmitting antenna uses about 232 radials. I have met one ham who had a vertical for 160 metres, which had that sort of setup. The reason being that he used to be the technician at the broadcast station. The broadcast station moved. They left the antenna and the earth mat behind, and because he had been the technician resident of that place where the transmitting site was, he bought the house and the antenna. So he now had a perfectly 160 metre antenna, pardon me, with 232 radials or whatever it was. And that's the problem with a vertical antenna. The closer it is to the ground, the more radials you need. If you have it up high, such as a thing like this, four radials work quite well, really do quite well. You can, the snag here is that has an input impedance of about 33 ohms. Now, again, you want to use that beautiful 50 ohm coax cable that you managed to get. So what can you do about it? Well, you can put in some form of a little transformer there, and that works okay, particularly for only working at one frequency. But a simpler way is to actually droop the radials down, like that. And in vertical, it looks like this, okay? And you can find a point where by suitably altering that angle alpha, you can come up with a feed point impedance of 50 ohms, which is very nice. I have a book which was written by a gentleman called Commander Lee, and he was a communications engineer in the US Navy. The Navy's very enthusiastic about verticals, but because there's not a lot of real estate on the ship, and you can throw up a vertical and you've got a viewed ground claim. You've got thousands of tons of steel underneath you, and it works quite well. But a better way, particularly if you're only, I'm speaking here, if you have an antenna which you want to use on one frequency. Now I'm particularly interested in 10 megs because it's a frequency that's working rather well at the moment, and I'll show you some photographs in a minute. this thing, about every decade or so I get out Commander Lee's book and I read it and I get very enthusiastic and I put up a vertical and it lasts about 3 months and then I take it down. So nowadays if I ever feel a vertical coming on, I go and make a cup of tea and take 2 Panadols and lie down and wait till the feeling goes away. But a better idea is not to use a standard quarter wave vertical, but to use what is called a folded monopole. What's the impedance at the centre of a folded dipole?
300.
Roughly speaking, 300. The impedance at the centre here is something like 70 ohms. The radiation resistance is more than twice what it is for the conventional quarter wave ground plane. And the extra effort that you put into that, I guarantee you, will more than justify itself in the results that you'll get. I don't think I will ever put up another conventional quarter wave vertical for high frequency, but I will definitely put up a folded monopole. That's what this thing is called, a folded monopole. It's a quarter wavelength high. Radials if you can make them, if not you need lots of metal. I'm going to put it on the roof of my carport, and because it has a much higher input impedance, it's a lot easier to couple to, and it puts more current into the antenna because it's easier to feed it. The losses are a lot lower and the performance is superb. It is worth the effort, gentlemen. Okay, I have not yet mentioned the folded dipole too much. Well, in fact, I haven't really mentioned it at all in this context, because it takes twice the amount of wire for a half-wave dipole. It has an input impedance somewhere about 300 ohms. It lends itself to being fed with a 4-to-1 balun, which is very easy to make. It works beautifully with coax cables, and it also provides more parking space for the birds. And if you're an animal lover, I suppose that's important. But the point is, though, with this thing dangling underneath it, they usually tend to sit on here, and that happens to be, a high current point. And I've actually seen birds doing this, and if you key the transmitter at the right way, you can see 15 birds doing this. Don't tell anybody I told you that. I'll probably find that the greenies will be lined up getting ready to break my windows or something. So, we've spoken about the design. You have to determine, first of all, the operating frequency, the length you require. This will tell you what you're going to do about your real estate. Now, I consider that probably the most suitable wire antenna for HF for amateurs is the VK2ARZ. I've spoken about that before. The results from those who have gone to the trouble of constructing one properly are, legendary. Now, the only snag is it's about 102 feet long, and lots of backyards are only 50 feet wide. They may not be much longer. Under the terms of the new agreement, which the Wireless Institute has kindly instituted on our part, we can now put up a maximum of 3 masts. They have to be 5 metres from the side fence, and they have to be totally behind the house. It goes all right for somebody who only wants to work on 6 metres. They can put up a mast in the centre of the yard and they're home and hosed. But if you want to operate on 80 or 160, it's very difficult. The question then is, what can you do about it? Well, when I had my G5RV up, it looked like this. it still works. And the length is not incredibly different. You don't need the full length. The full length is out here and out here somewhere. By bending the ends down, you can achieve the same result. So don't give up too easily. There are various ways of going about it. In my case, this was folded down mostly vertically, but about 4 feet to one side, because I had a halyard which was tied onto the top of the picket fence. Over in this end, it went first of all to the top of the mast which originally held my VHF antenna, and then it went over towards the fence, with a halyard onto the fence. It is always possible to get one up. You want to make it as inconspicuous as possible. This is where the design of the masts come in. Now, I'll pass these photos really. Okay. Send that one up to the back, please, and then just pass them all around. Okay, this is the base of my northern mast. It was given to me in 1962 by the late Horry Young, VK2ARZ. He was posted to New Guinea. He was going to lease his house, and he didn't like the idea of leaving his beautiful mast behind. It was made out of a single piece of Oregon, 4 inches by 4 inches, and that's the section you can see there. That's all 4 inches by 4 inches. It was tapered to the top. It was 30 feet long, and it was tapered and rounded, so at the top it was about 2 3/4 inches high. I've had that up now since 1962. About every decade I take it down for sanding and painting. Unfortunately, that is very difficult to do nowadays. Was it much binding in the marsh or the Goon Show? I think it might have been the Goon Show. There was a bloke who had this standard catchphrase, "You can't get the wood, you know." And that's the way it is. You try buying a piece of straight-grained Oregon, 30 feet long and 4 inches by 4 inches. If you can do it, please let me know. So that technique is now very difficult to achieve. So you've got to do something else about it. And the technique which I use now is to laminate the antenna and make it out of here we go. Pass it up to the back. Just send them around. You can achieve those longer distances by laminating bits of timber. And the longest that I could get that might attend was 5 metres. And I was able to obtain what we used to call 3x2, which is now roughly, well, it's 75 by 50 before they start planing it. But by the time they finish planing it, it's a bit smaller than that. But if you start off with 2 pieces, if you start off with 2 pieces like that, and then you cramp another piece in there like that, and you then put a piece down here, and you can put a bolt straight through it. That's in that view. In this view it looks like this. But in my case, what I have done, this last little section, I have let in another piece of timber. This whole lot is glued together with marine glue, and then I put stainless steel bolts through in here with very large washers on them. you have to turn the nuts up on the bolts tight enough to hold it, but not tight enough to crush the timber. Why do I use stainless steel bolts? Because bitter experience has shown me that the use of mild steel bolts, plated as they may be, eventually leads to disaster. And it works out this way. You have a piece of timber, you drill a hole in it, you put a bolt through it. Now, the timber, bless its heart, contains sap, even though it's been kiln dried. It also accumulates moisture from the atmosphere, regardless of how diligent you have been about painting it and so on. There will always be some moisture in it. The moisture then starts to attack the bolt, and the surface of the bolt becomes rusty. And that's only the start. The next thing that happens, it develops what's called dendrites. All these things. And they're like little bits of pine tree. You know, a bit grows out like that, and a bit grows off there, and 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 off there. And this is around the whole surface. And that starts to attack the bolt. And I've seen a 3/8 bolt, which was actually only about 1/8 of an inch in diameter, and the rest of it was made up out of dendrites. And it penetrates into the timber. And when you go to take it out, you can't shift it. The only way you can do it, you just keep turning it until you screw the nut off it. This is called wringing its neck. And then you can drive it out. But if you use stainless steel bolts, fix and forget. You know, I'm 84 now. I don't have all that many years to go. But what I do know is I won't be replacing those stainless steel bolts. And they don't cost a huge amount of money within limits. The one that I bought to go here to go through here was longer than the standard length, and I think the factory must have made it specially for me, because it costs a lot more money than I really wanted to pay. But, you know, you pay your money and you take the choice. If you want that performance, that's it. Why did I build it like that? I think I have yet, have I sent this one around yet?
Yep.
Okay, take a look at it and you will see that it's connected to the end of my shed, and it's connected there in two places. Now at the top we have, I think the piece of timber is it called the ridge pole? The one right along the centre of the roof. You know, you have your roof like this, and you have a piece of timber that goes in like that. And these are your, I think, they're called purlins, I think, and these things are called rafters. Anyway, you've got a piece of timber. It used to be 6 inches or maybe 8 inches by 1 inch. Now, inside there, I have installed, in plan view, here is your ridge pole. I have installed 2 pieces of steel, which are actually angle brackets that I was able to buy from Mitre 10. And it's so designed, I replaced these barge boards by timber which was about 10 inches by inch and a half. And the brackets sort of go out like that in here. Here's our barge board. There's our barge boards there. Now, when the antenna goes up, the antenna is here, and I have a piece of aluminium angle, which is about, I don't know, maybe 75 millimetres by 75 millimetres, and the thickness of about 10 millimetres. Very substantial aluminium angle. I went to, there's a factory near me, and I said to them, mate, I need a bit of aluminium angle, about this big and so on. If you got something in the scrap bin, oh, I'll have a look. So he went and he came back with a piece about that long, which was enough for me to make up an antenna tow bar fitting for my high frequency mobile, and leave a few bits over, including this piece here. So I now have stainless steel bolts that go through there, and the antenna is clamped. The fact that there's a hole there allows the water to go through. If you don't have that, it can accumulate around there and lead to all sorts of problems. The bugbear of amateur radio operators and masts is water 1, corrosion 2, avian terrors 3. Now, that supports the antenna here. And down here is the shed. Down here is the right angle bracket that you can see in that photo. And that bracket now consists of 3 pieces of timber, each one about 10 inches by 25 millimetres. And in plan view, it's roughly like this. The mast actually goes in here, out from the board, and there's a bolt which goes through like that, and then there are 2 brackets like this. Again, I got those from Mitre 10 about many years ago, and they are bolted into the timber piece which goes across here, which I have reinforced. It's not just the conventional end of the shed, it has other timber behind it which is bolted onto it to reinforce it. And the angle bracket is here so that I can undo this situation here, and the whole antenna will then rotate around. So it comes around like this and goes out like that. So the end of the antenna is out parallel to the carport, which sits just in front here. So the end of the antenna is only about 8 feet above the ground. That means you don't have to go up there to do something about it. But what I do is I have stainless steel eye bolts. You may be tempted to use a pulley. Don't do it, please. Pulleys are bad news for antennas. The halyards always jump over the edge and get jammed in between the pulley wheel and the side of the sheave, and then you've got to take it down anyway. The clue is that you use a stainless steel ring bolt. And your halyard goes up through that. Because it's stainless steel, it's nice and slippery. There is no end to it. The halyard can't. You might be tempted to use the garden variety ones that, they just click together. Well, finish up, the halyard will get through there. You can try putting it up there, but it doesn't make any difference. It'll still get caught. But by using a stainless steel ring bolt, you can put the halyard up and down, and that enables you to raise and lower the antenna. With this system, make sure that you have sufficient halyard so that when the antenna's out here, you've got sufficient halyard here so that the antenna is still within reach. It doesn't finish that you run out of halyard with the antenna in that position. That's not a useful situation. You must work out that you have sufficient halyard so that you can drop it right down to the ground. Okay, so now we've spoken about designing the location, designing the length, designing the construction. What is probably the most important aspect of the construction of the mast system? Safety. I don't know about you guys, as I said, I was 84 a couple of weeks ago. I don't really enjoy climbing on ladders anymore. I don't want to have to go up there to do anything about the antenna. I want to do it down here. And by using a design of this nature, you can drop the antenna down without having to, get yourself a skyhook and a harness and a parachute and a free ticket to St George Hospital. Safety is the most important consideration. The next thing that I've spoken about is corrosion and rust. The use of stainless steel hardware for the construction. Where you put a bolt through the timber, use the largest washer you can get. There are 3 sizes of washers for most bolts. There's a small one, there's a medium one, and there's a big one. Well, use the big one. It has the maximum possible diameter. It reduces the bearing pressure where you tighten the bolt up on the timber. When you tighten the bolt up on the timber, don't tighten it up to the stage where you crush the timber. You have to hold it but not crush it. I have also, because the bolt was longer than I needed, I've got a nylon washer in between the stainless steel washer and the timber. The nylon washer sticks to the paint, and the stainless steel washer on the nylon works like a beautiful bearing, so you can lower that mast down without any difficulty. I have discussed the dipole, the folded dipole, the loop antenna, and the folded monopole. Gentlemen, at this stage of the game, I think we'll call it quits, and if there are any questions, I'd be happy to take them.
How do you feed the loop? The
Beg your
delta loop?
pardon?
How do you feed the delta loop?
Okay, well, it's about 120 ohms. That's 120 ohms. You want to come out of the transmitter at 50 ohms. So you need an impedance matching system between 50 ohms and 120 ohms. Zm. Now Zm, as I explained earlier, the square root of Z1, Z2. Square root of 50 by 120. 1200 by 6000 ohms. Okay? What's the square root of 6000?
77.
7, 5, times 7, 5 equals 4, 3, 1, 2, 5.
What? No. No, 77 ohms.
Put 80 is 6,400, isn't it? So it can't be.
Anyway, I've made a mistake somewhere and I can't see well enough to see where I made it. But the point is that it works out at about 75 ohms. So you need a quarter wavelength of 75 ohm cable in between the antenna and the loop. And that'll give you a very nice match, remembering that you're designing this for use on a single frequency. Another way to do it, you could use 50 ohm cable all the way. Well, then you need an impedance matching transformer here to go from 50 ohms to 120. Now, 120 divided by 50 is 2.25 roughly, isn't it? So you need a transformer with a ratio of about 2.25 to 1, impedance ratio. Now the turns ratio is the square root of the impedance ratio. Or put it another way, the impedance ratio is the square of the turns ratio. It works out at 1.5 to 1. So if you have a transformer which has 3 turns here and 2 turns there, that's 1.5 to 1. You can wind that yourself by getting a toroid, and you use 5 wires and you wind them in parallel. Twist them together and wind them in parallel. 1, 2, 3, 4, 5. So you join that one to that one, that one to that one, and you've got that point there and that point there. The impedance between those two is 120 ohms, and the impedance between these two is 50 ohms. So you just have a toroid, you wind your 5 wires around there, you connect 3 of them in series, and the other 2 you take away with your 50 ohm cable. You can connect one end, you can connect the earth end to somewhere in the centre or even to an end, but it's all a bit haphazard. But nevertheless, that is the turns ratio which you need, 1.5 to 1, and it'll give you the correct impedance ratio transformation from 50 to 120 ohms. If you have a modest amount of money, you can buy one. There's a company over in the States, I think they call themselves Balance Solutions or something. You'll find it on the internet. And they make one of these special impedance matching balance which uses the two chord design. The first one which simply transfers 50 ohms to 120, and the second one which is a balance. You could use that thing in here and it would work perfectly. Another way is you can use any length of, no, I won't go there. That's the best way to do it, to use a 75 ohm quarter wave matching section in between the loop and the feed line. Okay, if you're finished with those photos, if you bring them back please, and we'll call it quits.
Thank you very much, Max.
Thank you very much.
I still believe non-resonant antennas as good as resonant.
Have you ever pushed a kid on a swing?
Pushing kids and pushing RF are two different things.
No, they're not. Exactly the same principle.
A cup of tea and biscuits if you want there, gentlemen.